Okay, now we're going to discuss compressible flow. Before starting the compressible flow, we need to be well aware about thermodynamics and first law of thermodynamics, second law of thermodynamics, and what is meaning of stagnation temperature, stagnation pressure, static temperature, static pressure, and etc. about uh, gamma. CB, CVs, R, BV equal R, all of this. Okay. If not, so we'll take these equations now for granted. Then after we're going to discuss later on the fundamental or the basics of thermodynamics and how we can, even all of these equations can be written in respect of first law of thermodynamics itself. Okay. It is way very simple. I will try to explain it in quick, but if it will be in deep, it will be in later sessions. Okay. In the compressible flow, we need to remember compressible flow, which is a Mach number, velocity divided by speed of sound, is less than or equal 0.3. It is incompressible, even it is air, even it is gas. Okay, we already discussed it. We are going to discuss it even in the dimensionless analysis. This approximation is valid because the delta change in the density, it will be less than or equal 5%. Okay. In any process or in any flow inside the ducts, inside ducts by any shape, we assume it is an isentropic process, which is mean the entropy doesn't change, and there is no heat transfer, which is mean there is no heat transfer chain. Okay, so from first law of thermodynamic, delta Q or dq equal du internal energy minus dw. We already discussed this one before, if we can remember, that the internal uh, and heat and work, and there is other form of which is can be discussed, but this is the first law of thermodynamics which will have been. Okay, work in case of no heat, which is mean it is an adiabatic process. Isentropic is an adiabatic process, but not all adiabatic process is an isentropic. So we can write that is change in the work is equal to the change of the internal energy, and the change of the work is BV dV, and its change of internal energy it is CV dt. And also we know that, by the way, a change of enthalpy is CB delta T plus, uh, if you have any change in the velocities for the entire. Okay, so based on that definition, B2 minus V2 B2 V2 minus B1 V1 will divided by gamma minus 1, because of gamma equal CB by CV, and we know that is B2 over B1 equal T2 over T1 gamma, power to gamma over gamma minus 1. Gamma it is 1.4 by the way, and gamma is CB divided by CV. Okay, this is thermodynamics. So based on this, you can identify the density, which is from BV equal MRT, based on this equation. This is this equation, and also you need to understand that is stagnation enthalpy is equal anyway. Stagnation enthalpy is assume if you have any container of anything, and this point with all of its energy has been let it to go in rest to a constant or to a zero velocity without any movement, without very slow, which is mean there is no any friction, there is no anything, so it will reach to a stagnation condition. The stagnation condition, because energy will never be destroyed or removed, so whatever you're giving energy, if you're giving return back isentropically, you will reach to the stagnation condition. So this point has a stagnation condition equal to this point, equal to this point, equal to any point, because it will return back. And the stagnation condition can be summarized as if you have a tank here, and the tank velocity inside is almost zero. And because this is the source for all of this, so the condition in the tank is a stagnation condition for all that one. Okay, so based on that, we know that is because of stagnation enthalpy is equal anywhere, so we can based on it can write uh, it. We're going to discuss it later if it's not clear about how we got this relation because where it is, yeah, because the stagnation 1 plus the velocity divided by 2 equals Salvi equal the stagnation plus velocity equal to, and we know that stagnation velocity is 0, so stagnation in Salvi is equal this term. So based on this term you will find velocities, and if the stagnation equals stagnation, or this one divided by this one, and we know that is the enthalpy is equal to U and the CB, so you can reach to this temperature stagnation over the temperature anywhere in the duct equal to 1 plus gamma Mach number. Mach number where is at the duct? Maybe under 1 plus 1, whatever. And also in the density, you can use this the same. And also in the, we know the stagnation temperature is always, it's just T gun here, that's it. Also, we can identify that is the Mach number is as a parameter of the pressure, which is stagnation over pressure at the exit. We're going to discuss this one later, but however, why I write pressure at the exit, but it can be any pressure by the way, okay? And we can also identify that stagnation pressure equals the pressure multiplies this number of Mach number, okay? Or this formula, okay? Also, we can note that we need to note that the speed of sound for the gas is changing based on what is the type of the gas and what's the temperature of the gas. Okay, it is gamma RT all under square root. Mass flow rate, of course, we know it rho V area, which is rho equal pressure over RT. Just this is an information. And R equals CB minus CV is thermodynamic. Okay, and we know that is BV power to gamma equal constant. This is for the isentropic process. This is how we got the gammas here. Okay, B over B equal constant. This is equal T over T, etc., etc., etc. Okay, okay. Now let's assume that is we have a converging duct. We know while we are making a converging duct and the area getting decrease, velocity get increased. When the velocity get increased, so it will reach to a position that it will reach to Mach number equal 1. And remember, even if you reach to Mach number equal 1, if you decrease the velocity more and more, if you're going to decrease the velocity, so decrease the cross-section area more and more, the velocity will not get increased. Why? I'm going to discuss it later. Okay? So if I assume that is at the converging duct, while the Mach number here equal less than 1, the velocity going to increase till it reach to Mach number equal 1. If it's Mach number equal 1, you just write 1. So we name, in case of converging duct, star, the star condition, which is temperature star, is the stagnation temperature with this number, and the stagnation pressure in this number, and density in this number. Okay? Okay, so let's go and we name this case is shocked. Nozzle is shocked. Okay, why it will never change? Because it is shocked. While the flow is shocked, so the flow cannot know what is after it. Okay, because the pressure waves is transmitted through a speed of sound. So if you decrease the area, so to know that, for example, I will assume we reach here to Mach number equal 1. And we start also to decreasing the area. So this slice, to know after it there is a decrease, a decrease in the area, so a pressure wave need to act, which is mean more restriction happening. So these slides need to know after, so the streamlines need to what? To get congested more and more. But because it cannot reach to the pressure wave, so what will happen? It will have more and so it will have what? It will reach to a velocity, yet the velocity cannot be increased because here cannot see what is after it. It doesn't know what is happening here. Okay, so it will reach to a certain velocity, and velocity will never increase. But if we need to increase the velocity over Mach number equal 1, it is very easy. We need to make a diverging duct. So we are going to increase the duct. You will tell me, okay, when you increase the duct, the velocity going to be decrease. No, the same concept. Because the velocity here cannot see after what is happening. But why the velocity is increased? It is due to that mass flow is equal constant. If this slice doesn't know what happened after, but when it is moved from section to another section, while it is already Mach number equal 1 or more, here 1, so while the area get increased by logic, by logic, mass flow is equal constant. So if the mass flow is equal constant and the area get increased, so density are going to decrease as the pressure going to decrease to satisfy the same. While you're doing the same, velocity need to increase because this decrease, this equal constant, is the velocity get increase. So diverging duct after Mach number 1, increasing the Mach number. Okay, so the pressure going to increase while the density going to decrease, so pressure going to decrease, so the density going to decrease, so the velocity going to increase till you reach to a pressure here very low, and you can discharge. But why I used very low? Because there's a limitation. If you start to make diverging till the end, so the pressure will go down. Now you have a condition. What? Maybe the pressure here is coming less than the stagnation pressure here. So the pressure here will go like this, and two waves going to hit each other. High pressure over than this pressure, so you will have shock with S. Shock at the diverging. So if the pressure here less than the stagnation pressure here, shock will happen anywhere. Okay? And when you have shock, so the with S, so the isentropic, because there is a clash between two waves, so the isentropic concept is not valid. So all of these equations is not valid after the shock at the diverging nozzle. Only the temperature is valid. Okay. Okay. طب my question is how to reach to Mach number 1 at the nozzle. If you check this one, so we need to ensure that B, B star, B star, which is the pressure here, is satisfied, which is mean you need to reach to this pressure. In another way, the back pressure, which is going to be here, because at the start of the flow, there is no supersonic here. So the flow here can see whatever it is here. So while the back pressure is less than the pressure here, so the flow will continue. So you can reach Mach number equal 1. And even the back pressure equal to pressure here, which is B star, which is to reach to Mach number, so also Mach number will happen. But if the back pressure bigger, back pressure bigger than the nozzle pressure at Mach number 1, it is impossible to reach to Mach number 1. Okay. And the same concept what we discussed here if the stagnation pressure here. Okay. So now we need to identify how to calculate the stagnation pressure. Stagnation pressure can be stated like it is open to atmosphere. So what is the pressure of atmosphere? Okay. Or you're giving it inside a pipe or whatever. So the definition. So the definition is pressure stagnation. back pressure stagnation is the back pressure, static back pressure, plus if you have any velocities, 1 over half of v square. Remember, you can use this one only if there is no normal shock. Normal shock, which is mean something happened here. Okay, so you need to know the stagnation pressure. Why I here write back pressure and here write stagnation pressure? See, back pressure here because it is a flow of, here is the flow, and this point can see the back pressure, can see it, it can see it. So it is the back pressure itself, the back pressure itself. But why we hear stagnation? Stagnation because this point cannot see this point, cannot see it. It need to see it while it rests, which is mean why there's a clash happen. So what is going to clash happen? The clash going to happen at the stagnation only, which is at rest. Here at dynamic, so it is okay. Here at rest, of course, there's no rest, there's clash. Okay, and this is a normal shock. Okay, so what is we're going to have that we discuss? That is Mach number. Uh, this is pressure, and this is length of the nozzle, and this is the nozzle location. So you have either no flow, pressure equal pressure, back pressure equal, or you have pressure drop, then pressurized subsonic, because pressurized because subsonic here, and the diverging duct, so pressure get increased because the area get increased, and also you have so also as well as here you can see it at A and B, it A no flow, B it is still under Mach. So what if the back pressure at C lower than B star? So at C the back pressure is equal to, let's assume it is equal to B star, but the stagnation pressure itself, but the stagnation pressure itself is at the back pressure is higher than the pressure. Okay, so what will happen? It will reach to Mach number 1, then it will reduce back again. Why? Why it is reached Mach number 1? Because the back pressure is low enough, to uh, reach to what's the name? Is low enough to reach to the whatever we are at. But still, it is not low enough to continue in supersonic. Okay, and point number E, F, and G, it is supersonic, but I'm going to discuss it later. What is E, F, and G? But obviously, that is the stagnation back pressure is less than the pressure what we have at the exit. So if I assume that is the pressure at the exit, at the exit here, for example, is 1 Pascal, and the pressure here is half Pascal. So yes, so the entire flow will be supersonic. Let's assume that the back pressure here is less than B star here. So it will be here sonic. But the stagnation pressure here is higher than the exit pressure. That is mean there is a normal shock going to happen. Okay? Okay. Now let's return back to another equation. If you're going to derive from here, from the Mach and etc., and you need to calculate the mass flow. The mass flow at any location, it is B stagnation at the tank here, if you have a tank, multiply by the area, multiply by number, etc., 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 till the end. Note that is maximum flow while at nozzle is Mach number equal 1. Why? Because if Mach number equal 1, we know that the pressure is P star. It cannot be less than it. And the rho is O star. And the T is T star, which is mean it cannot be something else. You get my point? Based on a certain temperature stagnation and, for the tank. So whatever you're going to do more pressure, if you do more pressure here will not change. It is B star, it is rho star, it is T star. If it is all fixed, if you go 10 peak, if it is all fixed, so M dot is fixed. So whatever you're going to increase the pressure here, flow rate, mass flow rate will never get increased. Okay. So at Mach number equal 1, so you can calculate what is the maximum uh, mass flow rate. Okay, so there is a maximum mass flow rate we can in case of shock. Okay, not normal shock, the shock. Okay, and there is another equation. It's very good to know it. It is named Workhorse equation. Workhorse equation. It is defining based on the above or based on this equation. So any area divided by area star. Area star, which is mean I know there is a converging, diverging duct, and there is a Mach number equal 1. Okay, at the nozzle. So at any area. So maybe here. What is the Mach number here? What is whatever here? Okay, you will find that the Mach number here is this area divided by area star. There's a long derivation for it, but you can divide this one. M dot is equal constant. So divide, make stagnation temperature is by. The only remaining in the equation is M and gamma. M is Mach, so it is 1 over Mach number, 2 over 2, or 2 over gamma plus 1, multiply, etc., till the end. But you will tell me, maybe this area is equal to this area. So I have two Mach numbers. Yes, you're going to have two Mach numbers because you have a square. So you have two solutions for it. So in case of, for example, area divided by area star is the minimum area, by the way, equal to, if you put it, try and error, I will make try and error for solution of such an equation, you will get what? You will get the first solution and the second solution. Okay, first solution you will find Mach number less than 1. Second solution is Mach number is bigger than 1. Okay, shall we do? Yes, if you have a calculator, can do trial and error solution. You write the equation and sometimes write the initial condition 0.001, then it will get for you the first Mach number, and write the second condition is 30 or 40, then it will give you the higher Mach number than 1. So you will have to, or you will go to thermodynamics tables. In thermodynamic tables, there is a Workhorse equation table, which is you can go check A over A while Mach number equal what is what. I am going to open it now. I hope this is very clear, and we can even go for the examples. We have 1, 2, 3, 4 examples. 1, 2, 3, 4 examples. Okay, I'm going to open the thermodynamic tables. External connection. I think this one here. This inside any textbooks you will find, for example, this refrigerant. I don't know what is R134. It is this for exchanger. We're going to discuss all of this later. Okay, in thermodynamic part. But I want to try to horsepower equation. Where is horsepower equation? Yep. Yes. Yes, horsepower equation. The horsepower equation and or whatever. So when you have A over A, so for example, this is A over A, so you can get what is the Mach number. Okay. For example, Mach number 1 for sure should be equal 1 A over A for sure. Okay. And continue based on it. For example, if you have A over A 25, so the Mach number is 5. Then you will tell me, okay, where is the Mach number less than 1? Okay, the Mach number less than 1, which is One second. I don't know where it is. Okay. Just I didn't notice before. It is start from 5 and going back again to 5, by the way. For example, this is 2.9 and this is almost 2.9. So at 2.9, this is 2.6 as the diverging duct, and it is zero point 0.2 at converging duct. Okay, if you have something in the middle, so okay, return to here. So check what is your corresponding function. For example, you have 2.9 approximately here and here. So you can check what is the Mach number here and what is the Mach number here. Okay. Why we didn't use no, this one another function. It is something else. We don't want to open it. We're going to open it later. Okay. But we need the Mach number itself because equation with the Mach number. Okay. By the way, this one, K is gamma. In some textbook K, some textbook is gamma. It's 1/4. This means it's for the gases. Okay, if it is not air, it's not air. If something gamma is different, voila, you need to do trial and error. And also, of course, you can use this to, if you want to, example like some complicated, and you need to take a Mach number. Okay, I write it here for more easy. But if you have the pressure, you have pressure note, you don't know what is a Mach number, either to calculate it or go here, pressure over P naught, P over P naught, check it, and you get a Mach number. Okay. Uh, that's it. Of course, when you have this P naught stagnation pressure, by the way, and of course this one, whoever will start at 1 equals 0, t, t naught at 1 equals, all of this should be at 1 equals 0, which is mean in case of the temperature equal the stagnation temperature, so we know that the velocity is equal to 0, and if the pressure equals the stagnation pressure, so we know this is equal to 0. Okay, just for understanding the curves, or we use the equation. Okay, now we can start with the first simple example